Now let's see how we can find probability of null set. Generally, we have P of S equal to 1 and we assume P of null set is 0 because since S union null set is S, because we have this union, that implies when I apply probability on both sides, we have this, and P of S union null set is P of S, applying probability on both sides. Now this being union gives me P of S this. This is plus because I'm using the axiom of additivity, which says this equals this. Now this P of S gets cancelled and I get P of null set equals 0. Therefore, probability of null set is 0 and probability of S is 1. These are called the trivial cases of the probability function, where we have P of null set is 0 and P of sample space S is 1 are the two trivial cases of the probability function P from P of S to R. For this probability function, the two trivial cases, this equals 0 and this equals 1. So let's take an example problem to study the probability function for a given mapping to be identified as probability function using the basic definition of this. So for example, I have if S equals 1, 2, 3, 4 is a sample space of the random experiment if S equals 1, 2, 3, 4 is a sample space of the random experiment zeta, then is the mapping P from P of S to R a probability function, is the question out here. So we have to prove this, or we have to identify whether this mapping is a probability function or not a probability function based on the three basic axioms which we have discussed in the definition of probability function: axiom of non-negativity, axiom of certainty, and axiom of additivity. Now in this case of the function to be proved for a probability function, the condition here is given to be that P of 1 is 0.1, P of 2 is 0.2, and probability of 3 is 0.3, and probability of 4 is 0.4. Now, let's prove that this mapping is a probability function based on all the basic properties. Initially, to start with, the axiom of non-negativity. Clearly, I find that each of P of 1 or P of 2 or P of 3 or P of 4, which are considered here, are greater than 0. I don't find any of the probability which is equal to 0 or negative. So therefore, that implies P of S to R satisfies axiom of non-negativity. Is how we identify the first property. Similarly, let's next identify the axiom of certainty, that is the second property of the probability function. Now next is axiom of certainty, where I would like to find the probability of sample space S and just see that if the probability is equal to 1. So probability of sample space is nothing but probability of each of the 4 events as given here. That is P of 1 plus P of 2 plus P of 3 plus P of 4, which are the 4 events taken out here. Therefore, this would be nothing but 0.1 plus 0.2 plus 0.3 plus 0.4, which when added gives 1. Therefore, probability of sample space S is equal to 1. That implies P from P of S to R satisfies axiom of certainty, is how we identify the second property of the probability function, axiom of certainty. Now let's prove for the third property in the similar manner. Now let's see the third property, where it is given in the problem that, now as defined in the given problem, P of E is defined as sigma A belonging to E of P of A, where E is an event subset of S. So with this basic definition of P of E given as summation this, let's find the third property, that is axiom of additivity. So therefore, E1 and E2 are events of E, are events of the random experiment zeta, implies P of E1 union E2 will be nothing but written in the form summation A belonging to E1 union E2 of P of A, as taken from the definition of this. I get this. Now this is nothing but, when split, A belongs to E1 plus A belongs to E2, through which I can split separately, because A belongs to E1 union E2 implies A belongs to E1 or A belongs to E2 as split. Now P of A, sigma P of A belonging to E1 is P of E1 by going by the definition of this, and this will be nothing but P of E2 as this. And also, I also see that E1 intersection E2 is null set, because our 2 events of this which are not intersecting, that is, they are disjoint events. Therefore, with this, I can say that P from P of S to R satisfies axiom of additivity, as how we understand the concept. P of S to R satisfies axiom of additivity. Now, therefore, the probability function or the mapping P from P of S to R, which satisfies all the 3 axioms, can be said as a probability function. Now since axiom of non-negativity and axiom of certainty, and next the axiom of additivity are the 3 axioms satisfied by the mapping P from P of S to R. Therefore, because of this, I can say that the mapping this is a probability function. So a probability function needs 3 basic axioms to be proved in series of steps, and hence for the given problem P from P of S to R is a probability function. Now here we have some properties of probability function which need to be identified. So in case of properties, first let me take S to be a sample space of zeta, which is the random experiment. So let S be sample space of the random experiment zeta. Now in this case, if P from P of S to R is a probability function, then the first property is that P of null set is always equal to 0, is the first property in probability function. The second property is if e power c is complementary or complement of event E, then probability of e power complement is 1 minus probability of E, is how we identify the property 1 and the property 2. Now next, the third property in the probability function is that P of E always lies between 0 and 1. This is true for all events E subset of S. So any event E, the probability is said to lie between 0 and 1 inclusive. We have already seen this in the limitations of the probability. The probability at the most can be greater than 0 and less than 1, and of course 0 and 1 being the trivial cases of the probability. So this is the third property identified in case of probability functions. Next is the fourth property out here. So the fourth property in case of probability functions is that E1 is subset of E2 implies probability of E2 minus E1 is probability of E2 minus probability of E1, is how we identify the property in case of probability functions. So probability of E2 minus E1 is probability of E2 minus probability of E1. Next, we have the fifth property which says that E1 is subset of E2 implies P of E1 is always less than or equal to P of E2. So these are the four basic properties identified in case of a probability function P from the power set of the sample space to the real numbers R, is how we identify the properties. Now next is the addition theorem on probability. This is one of the most important theorem which is applied in some of the problems of probability. So let's see what is the addition theorem on probability. So before this, if E1, E2 are two events of the random experiment zeta, and P from the power set of S to R, where S is the sample space, is a probability function then addition theorem on probability says that the probability of P of E1 union E2 is derived as P of E1 plus P of E2 minus P of E1 intersection E2 is how we derive the probability of union as addition theorem on probability. So P of E1 union E2 is defined as P of E1 plus P of E2 minus P of E1 intersection E2. Now here we have seen the addition theorem on probability. Let's see how we can apply this in case of some real life problems. So applications in daily life is when I see this basic problem where I want to find the probability. So let's see the question. The question says here, what is the chance of drawing a spade or an ace from a pack of 52 playing cards? Of course, the condition is that they are well shuffled. Now this question is purely based on addition theorem on probability, where the question says, what is the chance of drawing a spade or an ace from a pack of 52 playing cards which are well shuffled? Therefore, in this case, I want to find a basic concept of the addition theorem of probability which can be applied here, but before this, we need to have an idea of the rules of the playing cards. So now that we know that the playing cards are totally 52 in number, out of which we have diamonds which are 13 in number, clubs which are 13, and we have spades which are 13, and flowers which are 13, which account to 32. And out of this, we have 13 spades, out of which we pick the spades, and there are aces which are 4 in number. Each of them has an ace, one in this, one in this, one and this. So therefore, there are 4 aces because each of the ace with a diamond, each of the ace with a club, ace with a spade, and ace with a heart are the 4 different types of aces which we have among the 13 cards of each type. So with this knowledge of the playing cards, let's see how we can find the chance of drawing a spade or an ace from a pack of 52 playing cards. Now in this case, let me say the total number of cards being 52, the number of elements in the sample space is 52. So n of s is 52. And let me say the event E is drawing a spade and event E2 is drawing an ace. So with these 2 events, let's find the answer for the given question. So here, let E1 be the event of drawing a spade and E2 be the event of drawing an ace. So I have my probability of E1, which is Of course, here my n of E1 is drawing of a spade, which is 13, because there are 13 spades. My n of E1 is 13. But when I take an S, there are 4 aces. Therefore, n of E2 is 4, or the number of aces is given by event E2, which is 4. N of E1 is 13. And of course, I have my n of S, which is 52. So therefore, P of E1, probability of drawing a spade, is nothing but probability of drawing a spade from the pack of 52 well shuffled playing cards would be nothing but n of E1 by n of S, which is nothing but n of E1 is 13, n of S is 52. Is how we get this. So 13 by 52 is the probability of drawing a spade. Similarly, the probability of E2, that is probability of drawing an ace from a pack of well shuffled cards, would be nothing but n of E2 by n of S, which is nothing but the probability of drawing an ace is totally n of E2, which is 4, and n of S, which is 52. So therefore, P of E2 is 4 over 52. So probability of drawing a spade or an ace is given by probability of E1 union E2. It is very important to note here for the students that OR is referred as union and AND is referred as intersection. So if I want to draw either a spade or an ace, I find the union of the two events. So it is important to note that OR is referred with union and referred with intersection is how we understand the grammatical part of the mathematical definition. So OR is union and AND is intersection. So probability of drawing a spade or an S is P of E1 union E2, and by addition theorem on probability we know that P of E1 union E2 is P of E1 plus P of E2 minus P of E1 intersection E2 by addition theorem on probability. So using this, we will try to find the P of E1 union E2 with all the basic definitions here. Now that we have P of E1, which is 13 over 52, as we have found in the previous case, that is probability of drawing a spade is 13 out of 52, and probability of drawing an ace is 4 over 52. Now, what would be the probability of drawing both a spade and an ace is the biggest question. So if I want to draw a spade which is also an ace, let's see how we can find out that. Now, as we know that there are 13 spades and 4 aces, there must be one spade which is an ace, or there is one ace which is a spade. So therefore, there is only one possibility that a card is both an ace and also is a spade. So here we find that since the number of cards which are both an ace and a spade is nothing but number of cards which are both ace and spade by total number of cards, which is 52. So in this case, number of cards which are both ace and spade is only one possibility, because there is only one card which is of the form of an ace and a spade. So 1 over 52 is P of E1 intersection E2. Now using all these three basic things, let's find the P of union E1 union E2 using the addition theorem on probability. Therefore, now we have P of E1 is 13 over 52, P of E2 is 4 over 52, and P of E1 intersection E2 is 1 over 52. So using these, therefore, P of E1 union E2 is P of E1 plus P of E2 minus P of E1 intersection E2 using the addition theorem on probability. So this on simplification gives us 52, 13 plus 4 minus 1, and this is 13 plus 3, 16 over 52, or 2 eighths, 4 fourths, 4 over 13 is the chance. Therefore, I get this to be 4 over 13, which is the answer. That is, therefore, probability of drawing a spade or an ace is 4 over 13, or this is the chance of drawing this out of the pack of 52 cards, is how we get using the addition theorem on probability, one of the applications in the playing cards. So as in the previous problem, we have identified that OR is union and is intersection. Similarly, there are many events which we have to identify through the set theoretic description. So let's see some of the events which are understood in the form of set theoretic description, which is essential because when you solve the problems, we need to understand the mathematical part of the given problem in general form. Say for example, if I say A, B are two events, then the set theoretic description of So for this, if I say event A or B to occur, because here it is OR, then immediately I see that it is nothing but A union B or B union A, which I need to find. So for an event A or event B to occur, for drawing a spade or an ace, then we represent that as E1 union E2 or A union B, is how we understand the first property. Now this is AND, because I have AND here, I have the set theoretic description of the two events being A intersection B. So OR is union, AND is intersection, is how we identify the two events A or B to occur, A union B, A and B to occur, A intersection B. Next. Neither A nor B to occur. Now this is neither A nor B, that means it should not be both A and B. So this is A union B whole complement, is how we understand. But we know that this is A complement intersection B complement, therefore this or this indicates neither A nor B to occur. The next is A occurs but B does not occur. So when is the possibility that A occurs and B does not occur? That means B does not implies the not is attached to B. So A occurs but B does not occur is identified as A intersection B complement. Is how we identify A intersection B complement, or this is also denoted by A but not B. So these are the ways to represent A occurs but B does not occur. That means it's only A but not B. This is also referred as only A when we represent this in the set form. The next is exactly one of the events AB occurs. Exactly one of AB occurs. So let's see how exactly one of AB to occur I get. So this is A intersection B hook complement, that is A complement union B complement. So exactly one of AB to occur, then mathematically it is A intersection B whole complement or A complement union B complement.